Okay, good morning or afternoon or evening, everyone. DCT 302, class number 4. And 300 level means that it can be complicated. And today, it's going to be pretty complicated. We've already covered off in class 1 the overall ACEs block diagram and talked a little bit about power function and log coding at the front end and a little bit about 3 by 3 matrix transforms. In class 2, we did contrast, the code 100 issue, perceptual uniformity in picture rendering, and a big discussion of bit depth. Class 3, quasi-log coding, which I think is a big deal. So quasi-log coding is kind of the amplitude coding side of digital cinema, HD, VFX coding. Now I'd like to switch over and do details on the color side. So it goes like this. And now some of you might have attended DCT 301 a year ago, and I'm not sure how that breaks down. But for those of you who did attend or review DCT 301, this will be a refresher. But I'll have a somewhat different take on it. And it doesn't hurt to hear it again because it's all pretty complicated. And I'll be mentioning ACEs as we go through and talking about how these different elements relate to ACEs. So digital color starts in 1666 near Cambridge when Isaac Newton did this experiment with the prism. And it was Isaac Newton that figured out that color is not actually in physics. Color is in the brain. And there's some physical relationship, obviously. It has to do with the spectral sensitivities of the photoreceptors in the eye. But the key observation is color is uniquely human. It's completely different for animals and uh, insects and fish and so on. So we have 3 channels, obviously. We all know that. And let's explore how the light spectral distributions of physics map into perception, because we're going to code these things up in 3 channels. Now, we can measure the physics with an instrument, and this is a kind of expensive instrument, a telespectroradiometer. And I don't own one of these, but several of my friends do. And with a TSR, or a spectro instrument, you can measure the spectral distributions that are out in physics. And so here we have a graph of wavelength across the visible portion of the spectrum. So from about 400 to 700 nanometers. Longer wavelengths goes to IR, and then it goes to microwave, and then it goes to radio waves, but we don't see any of that. And shorter waves goes to ultraviolet and X-rays and gamma rays, and we don't see any of that. So the portion of the spectrum that's interesting for visual purposes runs from 400 to 700. And a spectroradiometer can measure the energy in these various bands. And I'm showing you here, just for the sake of example, the spectral content of the standard D65 white. So it's relatively uniform across the spectrum. And that's all that matters for our purposes at the moment. Now, the PR650 that I showed you a moment ago can measure power in 10 nanometer intervals. And so across the range from 400 to 700, there's 31 bands of energy. And you could potentially digitize each one of those 31 channels, convey it to a distant device, and then have 31 tuned dye lasers. And you could recreate at the far end of the system an approximation of this spectrum of D65. However, you don't have to do that, because we only have 3 different kinds of color receptive photosensors in our retina. So if only we could determine the correct three distributions, 3 channels would suffice. So let's try to figure out how to do it with 3 channels. Let's use as our canonical example a leaf, which is, I digitized this 20 years ago in California. It was the closest thing that I could find to a maple leaf, but it's not actually a maple leaf, that being the national tree of Canada. But it's got some reds, some oranges, some yellows. I'll use those as my examples. So let's try to figure out how we could build a scanner or a camera, and those are both more or less the same thing, except a scanner needs a light source, that will take this range from 400 to 700 nanometers and parcel out the short wave energy, the medium wave energy, and the long wave energy into 3 components that we can call red, green, and blue. Now, keep in mind what we'll do for the next, well, this entire class, actually, until the very end. We're going to be measuring linear light amounts of energy from normalized from 0 to 1. So we're not dealing with this perceptual notion of 18% mid-gray being perceptually halfway. This whole discussion is just linear light, or if you like, scene referred in the ACES terminology. So we send off to our filter designer a request, build me 3 filters that partition 400 to 700 nanometers into 3 chunks. And the filter designer is likely to give you textbook filters with really uniform response in the wavelengths of interest and rather rapid transitions on both sides for each of the 3 channels. And when you, so take my leaf, now pretend for a moment that the orange stimulus is quite narrowband and the red stimulus is quite narrowband. In practice, those stimuli, the reflectances from the leaf, will be fairly wide. But just bear with me while I explain this. Pretend that they're narrow and scan the leaf under the scanner. And you can see pretty clearly that there will be no energy in the so-called blue or the so-called green regions of the spectrum, and an equal amount of energy in red. So the problem here is that this scanner is reporting 0, 0, 1 for both of those colors, even though we see those colors being different. That's a big problem. The scanner cannot distinguish those 2 colors. So this is a failure. Try number 1, it's a failure. So let's send the request back to our filter designer and say, you really need to be more selective in your wavelengths so that I can parcel those out into different amounts of energy. So the filter designer comes back with a set of filters that are narrowband. If you like, you could call these wideband. And the narrowband filters now do distinguish the orange from the red. So the red will be reported as 001. The orange will be reported as 000. But wait a minute, 000, that's also black. So although we repaired one problem, we created another. And this set of filters actually doesn't work. Now, if you carry this argument to its conclusion, you realize that we don't really have a recipe to determine what those filter sensitivity curves should be. But we do have a test, whether they succeed or fail. And the test is whether the scanner, or for our purposes, what's more interesting is camera, reports different triplets whenever we see those colors as being different. And whenever we see those colors as being the same, the camera reports the same triplet. That's the test. Now, I'm not going to go through the whole huge long story. That would be a 10 class course on itself. But what I will tell you is the final result after you reason and experiment this all the way through is a set of three curves. And I'm going to call those long wave, medium wave, and short wave. And that's or LMS, uh, expressed the other way around. And that's the terminology that a color scientist would use or a vision scientist would use. These curves mimic the cells on the retina. And even though the whole assembly here of sensing curves is rather complicated, the important part is that the orange stimulus reports, well, actually it reports a little bit of the medium wave channel here, and the red stimulus reports these two values, a little tiny bit of the medium. Neither of those reports any shortwave sensor, but the numbers that are reported by a camera built with these filters would accurately distinguish all the colors. And that's what's important for us. Now, let's talk about these in terms of camera sensitivities. And the first thing you think is, well, I'll just build a camera, I'll use those curves. But, and in principle, in theory, that would be fine. And that would be a camera that delivers perfectly good color values. But there's a practical problem. And let me go to the next slide, which is just a magnification of those three curves. The practical problem is that there's so much overlap. And let me pick a color that is not on my chart here. There's so much overlap between the long wave and the medium wave that this turns out, this overlap turns out to be really bad for noise performance. And for those of you who got through 3 or 4 years of undergrad mathematics, it's the fact that the signal is correlated, but the noise is not correlated. So the noise adds up in an undesirable fashion. So for a practical camera, we do not use filters like that. What we do in a practical camera is move the red over 20 or 30 nanometers, putting the peak of the red maybe at this point. So a practical camera would have a red sensor that would look something like that. Now, we don't want to go too far into this region because from about, well, we can't see beyond 700. But the trouble is IR lives up here. And if you kind of accidentally or even deliberately extend your red response out into the IR region, then you run the risk that IR energy in front of the camera in the scene will be reported as red. And the worst case here, well, I'll tell you the worst case in a few minutes. The worst case is cobalt blue colors, and they run the risk of turning purple if you don't address this IR problem properly. So practical cameras move the red over. They suffer a little bit of a color reproduction error as a consequence of that, but they have much better noise performance. Now, those are the cone responses, the LMS responses, but it turns out to be highly advantageous for color purposes if we choose one of the three color science channels to be the luminance response. Now, I've normalized this graph to show the peaks all at 1.0, but in fact, the blue channel is amazingly insensitive. It actually looks like that. And the red and the blue are, or I should say long wave, medium wave, are sort of comparable. But it's really, really useful to have one channel be luminance. And the sensible channel to use is the one in the middle. And so what we do is we mix those three components together in the proper portions to get relative luminance, big Y. And that changes the picture somewhat. And then it's also advantageous to make two other channels, um, which in some sense, the color component is represented in those three channels, but the luminance has been removed. And those are the X and the Z channels. Now, so what we're doing here is we're going to do a transformation, and it's a 3x3 matrix. Now, you never end up using that 3x3 matrix explicitly anywhere in your VFX or signal processing or even camera processing, but it sits in the chain at a theoretical level, and it's very much part of the color science. So let me show you how that mapping into XYZ space works. It looks like this. So here we have, and the fact that the Z channel is way up at a high value on the scale, don't worry about that. These three curves in this presentation have been normalized for equal area, but it's another story how we get to that normalization. The key point is now, although I've drawn it in green, and actually I realize that's a mistake. I shouldn't make that green. I really should plot this in gray. This middle curve is the spectral sensitivity of luminance. And the curve we symbolize by a bar on the top of the letter. When you take energy in a real scene, and that energy might look like this, and you weight it under that curve, you get luminance. And the other two quantities, weighting the energy under this curve gives you big X, and weighting the energy in the scene under this curve gives you big Z. So now we've got three scalar numbers. Now we need those three scalars for each pixel in an imaging situation, but those now represent color. Now don't worry about the bump. That's not a feature of the response of the retina. That's just a consequence of the mathematical normalization that leads to that space. So the XYZ space is the fundamental space of color science. Now we're going to end up using RGB sensors, and they have a relationship with these spectral curves that's another 3x3 matrix. So we end up having several 3x3 matrices in the linear light domain, either in the kind of conceptual mathematics behind the block diagram or in the block diagram itself. And this is very much, very, very much tied up with the IDT component of the ACES workflow. And you have to understand all this business I'm showing you in order to build IDTs. Now, I guess you're hoping in the short term you're not going to have to build them, you're going to get them somewhere. But I'm imagining you're participating today, maybe not so much to learn how to build them, but to really try to get a grasp on what they're doing at the conceptual level and how they relate to color science. Now, you can do measurements of human beings to determine the response of human vision. You get different results for different observers, and it's important to keep in mind that color science is really based on an average of a lot of observers. This particular slide shows 49 observers, but the color science is basically an average which yields what we call the standard observer. Now, it's a statistical fiction, but the standard observer is the observer whose numbers are written up in numeric form in the standard, and that's how we do color science. So what it boils down to numerically, or if you like in linear algebra terms, is we take linear light spectral measurements from the scene, and let's say for the sake of argument there's 31 of those, and then we just take a dot product with these three columns, which are the X bar, the Y bar, the Z bar weighting functions, and that yields the three numbers that describe that color. Now, then there's another 3x3 transform which is it's actually a dot product with just a 3 by 3 matrix. And you can relate the XYZ sort of core color science system to the LMS that human vision senses, or to the RGB system in various flavors. Now, there's different flavors of RGB. There's 709 RGB used for HD. There's P3 RGB used in digital cinema, and there's ACES RGB used in the front end of digital cinema acquisition. These are different flavors, so they've got different 3 by 3 matrices. Now, we can't easily plot on a piece of paper, or in fact can't plot at all on a piece of paper, 3 coordinates. So we do a mapping into 2 coordinates that has arithmetic looking a little bit like the perspective transform in computer graphics. And this transform, the previous transforms that I've been showing you that have got matrix multiplications, a mathematician would call these affine. This transform, because it's got this division operation, is called projective. And it is very much the same mathematics that's used to make a 3D perspective projection. So that's the transform to little x and little y. And now you can see that the case of these letters matters. So I'll often talk about big X, big Y, big Z, and little x, little y. Now there is a little z or z component, which is the obvious sort of third element of this sequence. It's big Z divided by big X plus big Y plus big Z. But if you work out the mathematics, you figure out that little z is just 1 minus X minus Y. So actually, we never need to compute that. And whenever we need it, we just compute it from little x and little y on the fly. Now, there's a very simple way to come out of that mapping to go back to big X, big Z. And the advantage of going into that mapping is it allows us to build this diagram. So we plot on a piece of paper basically all the colors. Now, all the colors are within this horseshoe-shaped boundary, which is basically what's called the spectral locus on the outside. And that has all of the lasers. They all plot. They're as colorful as you can get. They all plot on the spectral locus. Then this feature is called the line of purples because it's mixtures of red and blue, but it takes a mixture to produce a color down in that region. A single wavelength won't do it. The single wavelengths just trace out the spectral locus. So this diagram represents the extremities of colors. And places here that lie outside that bound, these are not colors. Now, if you wish, I'm okay if you want to call them imaginary colors, in the same sense that, I is the square root of -1. I mean, you can't take the square root of -1 in real numbers, but we've got this whole system of complex numbers based on this imaginary component. So you could think of points outside the horseshoe as being imaginary colors, but they're not colors. Now, we can use them in math, and it works out we do use them in math, and I hope some of you remember from class 1 that the ACES blue component is actually down here. It is an imaginary primary, and actually the ACES green component is also imaginary. It lives outside the spectral locus. ACES red turns out to be real, and it lives down at that corner. So these quantities that are imaginary are useful for math, but we can't actually make or see those colors. What this diagram contains is all the colors. Now, the features in that diagram, I've shown you the black body locus. Sorry, I've shown you the spectral locus already. Um, that's here. I've shown you the line of purples. If you're drawing this on a napkin, it's useful to know that this boundary up on this portion of the diagram is just 1 minus x. White lives somewhere roughly in the middle of that diagram, but there's no unique perceptual definition of white uh, or physical definition. It can move around. So, there's different white points. My favorite goes by a CIE standard called D65, and that's the one we use most of the time in imaging. But those of you who understand cameras know that it's very common to get a camera uh, viewing a scene that's not lit at 6500 Kelvin, but might be lit by tungsten at as low as 2800 K, or even outdoor overcast, cloudy day, which might be 10,000 K. So color temperatures are used to describe common white points in imaging. And if you take a piece of metal and heat it up by passing an electric current through it, and of course this might be in the shape of the filament of a light bulb, if you heat up a piece of metal, you can relate the color that it emits to the XY coordinates of the chromaticity diagram. And there's some laws of physics that say that all of the colors from a hot piece of metal lie along a certain trajectory within XY coordinates. That's called the black body locus. And most of the illuminants that we use in imaging lie on or close to the black body locus. So we can choose a white point that lies along that locus, and D65 is pretty close to the black body locus. Okay, so those are the major features of the XY chromaticity diagram. And that diagram is used not only for imaging, but also other industrial applications. So you can plot where traffic light colors live on that diagram. And when you look at this is the actual standard for signal lights. And when you look at this, you discover something interesting, that a red traffic light has got to live in this region here. Blue traffic light, and that's maybe not so common in the US, but in Europe we use them for police cars. They have blue flashing lights. In Canada we use them for snowplows. But blue, or really that this diagram actually comes from railway signaling, where they use blue lights for I don't know what. But notice that the region for green is a huge area of the XY diagram compared to red, or even compared to blue. So you might ask, why is that? Like, how come you got green all over the place? Well, the reason is that moving from one color to another in little x, little y space may cause a noticeable color shift or may not. So basically here, I've just sketched out moving 0.05, because here's 0.1, right? So I've made a shift of about half that. And if you make a shift in green of that magnitude, you probably won't even see the difference, or would see a little tiny change. But making a 0.05 change in the red region can move you from red to orange. There's a huge change. So the little x, little y numbers, they're totally useful for science, but they're not very useful for imaging, because we'd ideally like to have an imaging system that takes red from 0 to 1, and I won't change pens here, but green from 0 to 1 and blue from 0 to 1, but it's got roughly the same perceptual shift in all three components. Now, we already talked about that in great detail in class 2 in terms of the 18% gray card living halfway up the perceptual scale. And that's all about those curves we use for each channel, a gamma correction or log curves. What we're talking about now is how does that relate to color space? And so let's march forward and talk about that. First, though, we need to now do the key fundamental conceptual notion of how to make color. We've talked about how you sense color, how you take the real world and you collapse colors into three components. Now let's talk about how to take three components and mix up colors in a display device at the other end. So one way to do that is additive mixture. And additive mixture works by taking three rather pure colors, and we hope that they're individually red, green, and blue. And each of those colors has got a spectral distribution associated with it. So the blue is obviously concentrated on short waves. The green is concentrated on medium waves. Now the red, you can see, looks a little odd. I'm using real data to make these drawings, and I admit it's out of date data because it's data from a Sony Studio Video CRT. And they used phosphors, which had rather odd chemistry in the red channel. But it doesn't really matter for human vision purposes what the spectral distribution is, as long as it integrates under those three curves to the right amount. And the red, it's a perfectly reasonable red, even though it's got these two narrowband emission peaks. Now, what we do to mix colors is take a certain amount of blue, a certain amount of green, a certain amount of red, and mix them together. And the common way of doing that today is we make a little red, a little green, and a little blue subpixel on the surface of a display device that's got a couple of million pixels, say, for HD. And if you use a loupe or a magnifying glass or a macro lens, you can go and very easily see these individual red, green, blue components. But by the time you look at that from 9 feet away, they all average out in your eye. You can't see the individual elements. So the addition in additive mixture in this sort of scheme comes from averaging in your eye. Now, there's other ways to average. You could put the red image up for a 200th of a second, the green image up for a 200th, and the blue image up for a 200th. In other words, you could time multiplex colors. And modern displays sometimes do this. Well, obviously, I think you know that a DLP office class projector does this. It does this with a spinning filter wheel, red, green, and blue filters spinning around, and just one DMD imager device. But another way you can do this is LEDs can be turned on and off so fast you no longer need the spinning filter wheel. You can just flash LEDs. Now, in this case, the additive mixture is coming from your eye adding these things up in time. And the other way to do it is just to have three complete imagers producing red, green, and blue simultaneously, and then have a set of color filters that optically mix those together. The addition in that case happens in the optics, not in your eye. But no matter how you choose to do it, and there's lots of different ways to do it, the mixture is taking place additively. Now, the other way that you can add is by starting with light that's rather uniform across the spectrum. And here I'm showing you D65 again. And then selectively removing some amount of short wave, removing some amount of medium wave, and removing some amount of long wave. And here I'm showing you the spectral curves of Kodak dye used in release print cinema film. So you get a spectrum that results from this removing each of the three bands, and that produces a color, and you can get a wide range of colors by using different mixtures. However, there's a tricky part of this formation of mixtures. If you think of taking a 0.5 ND filter, so an ND filter that just passes half the light, and then placing on top of that another identical filter passes half the light. Here where they overlap, you don't get zero. The arithmetic going on is not 0.5 minus 0.5 equals zero. The arithmetic going on is not subtraction. What's going on here is half times half is a quarter. The arithmetic is multiplication. And what goes on in subtractive reproduction is multiplication wavelength by wavelength by wavelength. So really I'm saying this, it's subtractive in quotes, but it's really multiplicative math that describes the mixture. Now, it's an extremely complicated part of this mixture that the cyan filter, to pick just one example, certainly removes long wave components, or if you like, it removes red. But it also removes an incidental amount of short waves. And that problem is even worse in magenta, where it does remove medium waves, but it also removes short waves. So there's interaction among the channels, which is highly nonlinear. That makes the math complicated, that makes the colors not easily predictable. So for the rest of the discussion, we'll just stick with additive color systems, because honestly, those are the only important ones in the modern world. So to give you the picture in color, you can imagine taking 3 colored filtered gels, putting them over 3 spotlights, and pointing them at a white wall. Now, you have to do this in a dark room, and that's one of the kind of paradoxical things about additive colors. You really start with black, but you can't make the screen black, so because then it wouldn't reflect anything. So you have to make the room black instead. Or in the case of a direct view LCD, you try to make the LCD as black as possible when viewed under normal viewing conditions. When you pull the power plug out of the wall, the LCD display looks black. And it can't get any blacker than that physically. I mean, there's some visual phenomena that might make it look blacker as soon as you put some picture material up, but it needs to start with black. And then you point the red spotlight at it, you point the blue spotlight at it. Where they overlap, you get magenta. So magenta is obviously the sum of red and blue. Where green and blue overlap, you get cyan. If you wish, you could call that turquoise. If you wish, you could call magenta purple. What is not at all intuitive is that when you mix long wave red and medium wave green, you get yellow. And that's not intuitive because it turns out that human vision has got a perceptual channel back in the brain dedicated to yellow. I mean, it is absolutely not a primary color. In terms of additive mixture, it's a mixture of red and green. But that mixture is not intuitive. We never see a greenish red, and we never see a reddish green. I mean, we can see reddish blue. I mean, in a sense, you could call magenta reddish blue. But this yellow is a very interesting phenomenon. Now, where all 3 overlap, of course, we get white. Now, let's go over and do so-called, quotes, subtractive mixtures. There, the largest range of colors is obtained when you in fact, let me switch forward to the next slide because there's a graphic for this. Here's the graphic. So the cyan filter basically removes long waves. So in a sense, it's minus red. Don't take that too literally, but in some sense, it's minus red. The magenta filter removes medium waves. In some sense, it's minus green. And the yellow filter removes short waves. In some sense, it's minus blue. So these things are related as C, M, Y are related to R, G, B. Now here I'm laying them out in what you might think is the reverse order, but I'm going from shortwave 400 to long wave 700. This is in wavelength order. So if you remove the long waves, you get short plus medium. In other words, you sort of get blue plus green, which is cyan. But removing the long waves is done with a cyan filter. That's one of the subtractive primaries. Yellow is another subtractive primary. Remove long wave, remove short wave, you're left with green. And similarly, you remove medium wave, remove long wave, you're left with short wave, which is blue. So that's the mixtures that you get from subtractive mixture. Okay, so far so good, but looks like we're not going to get quite as far as I planned to this class, but we'll keep going for another few minutes, and then I'll invite some questions and discussion. So get your questions ready on the chat line if you like. Okay, now we can plot into the little x, little y diagram the triangle of 709 RGB. And 709 RGB is physically realizable. We can make those primaries individually. Now, that's unlike ACES, which has non-physical primaries, as you remember living out here. So ACE, just for mathematical purposes, you can't actually make ACES colors physically. But you can make 709 colors physically, and later on in the class, I'll tell you about D-cinema primaries, which extend somewhat further than 709, a little bit like that. So we can plot the primaries on this diagram, and these primaries can be made. We can make all the colors that lie within or even on the edge of that triangle. Now, it's important to keep in mind that when you see these two-dimensional diagrams of color space, there is a third dimension, and that third dimension is the luminance. So it's not the case that you can cover all of those chromaticity coordinates all of the time. As luminance goes up, and here Walraven, our famous Dutch color scientist, is showing you luminance going up here, and the color range gets limited, like so. I mean, by the time that you're at white, there's no place to go. So your color range gets more and more limited the closer you go towards white. If I'm not mistaken, this is yellow, and it looks almost as high as white just because it's a perspective transformation. Here's magenta. Here's blue, which is very dark. You know, in 709, blue has got a luminance only 7%. So if you want to get blue brighter, you're already maxed out on the blue channel at 7%. The only way to get it brighter is add some green or add some red, but obviously that changes the color. So the key point is keep in mind the triangle down here on the two-dimensional plane doesn't tell you the whole story. There's a shrinking of the gamut as you go further up on the luminance axis. Now, some of you might have messed around with color management systems. If you've got a Macintosh, you've got immediate access to looking at different color spaces. And here you're looking at Adobe RGB, which has got a somewhat wide gamut. You're really just calling out data from the ICC profile associated with Adobe RGB. But this, like the XY diagram, is a vertical view into color space. And this space is projected in LAB coordinates, which officially would be CIE, L star, A star, B star, also known as CIE lab, sometimes written with a space, sometimes without. So here we're looking at it straight down on the A star, B star axes. And the story here is that these points are at different L star levels. And L star is related to luminance. Well, my approximation is L star is luminance to the 0.42, and you had that story earlier in the course. So there's tools available for you to go and explore these color spaces, and that tool from Apple is a particularly good one. And you get a relationship to the spectral locus in diagrams that look like this. Okay, so we're at 48 on the hour. So I'll just give you the preview of what we'll do next. We'll talk about black body radiators because they're an important source of illumination for digital cinema and HD. We'll talk a little bit about white balance and a few more illuminants, a little bit of the lightness arithmetic. And then I'm going to show you how it's pretty complicated to get into lab space, but I really do want you to recognize how that's an important space to understand the perceptual character of color space. So let's wrap there. You know, I'm kind of giving myself license to go for an hour. So we got, if we like, we have about 10 minutes for questions if you wish. Go ahead. So either by text, chat, or by audio, whichever you like. Oh, Peter Rixner is suggesting, last time I offered to pick up on the camera f-stop explanation. Can we continue next time? I didn't quite get the difference. So yeah, I have actually been sitting at the cafe working up a presentation on that f-stop thing. So, you know, I can tell you one of the great pleasures of teaching is you learn stuff. And so the other day when we talked about that, I learned a lot about f-stops. Well, mainly I learned how to explain it. But Peter, let me defer that explanation to next time. And I will show you a bunch of new f-stop material. And what I'll do is I'll plot that f-stop business onto the logarithmic scale from 0 to 1,000 that I used, what was that, class 2, or maybe it was class 3, that I used to explain the 1,000 to 1 ratio on the exposure scale. So let's defer that one. Anyone else with questions, comments? Okay, maybe not. Now, I must admit I did not get a chance to get to the forums this week. So there may be a few forum questions out there. I will go and visit the forums later today and catch up over there. And you're welcome to go and discuss things in the forum. And, you know, we can have some interaction there as well if you like. So coming back next time, more deep color science 300 level. It's been a pleasure. I have a lot of fun doing this. And let's wrap there for class number 4. Thanks all.